Now we're going to talk a little bit about energy. We've done a lot of work with matter, anything that has mass and takes up space, and now we're going to talk about energy. That's the things that don't qualify as matter, causing things to happen in our world. Energy. It's the ability to do work, cause change. It's moving, pushing, pulling, causing things to happen. As you see, we have the gerbil, who is going to be using energy to turn the wheel. That wheel is moving, it's doing work. And here we have a change that's created. This is some electrical energy, some plasma causing the gas to excite and glow, causing change. Work occurs when a force causes an object to move in the direction of that force. That is the actual definition of work as a scientist. Work is only that. You can't call it work if something's not moving. Work and energy are expressed in joules. That's a capital J. It's a new unit for us to measure things and talk about things in. Energy and work expressed in joules. Okay, so let's start talking about the kinds of energy. First, kinetic energy. Kinetic energy is the energy of motion. When things are moving, those things are said to have kinetic energy. Kinetic energy is based on the mass of an object, and it is based on the velocity of an object. So, the bigger or more massive an object is, the more kinetic energy it will have. The faster it's moving, obviously, the more kinetic energy it has. Okay, as you look to the formula on the bottom of this page, the formula is kinetic energy is equal to the mass times the velocity squared divided by 2. So clearly, since you are squaring the velocity, the speed of an object or its motion has a greater effect on the amount of kinetic energy it has. Once again, kinetic energy depends on speed and on mass. This is the formula for kinetic energy. You need to make sure you have that formula written down. We are going to work with that formula multiple times. Mass multiplied times the velocity squared divided by 2. And once again, kinetic energy is expressed in joules. That is a measurement of energy. Potential energy. Potential energy is something that an object has because of where it is, such as this roller coaster is very high. That means it has the potential to drop and speed up, has the potential to move, has the potential for some kinetic energy. This is a spring because of its shape, because of the way you can squeeze it and then it can hold on to that energy, and you can release that energy because of the shape of the coils. Is said to have potential energy as well. And you can see the transfer of energy. Here's some kinetic energy that's causing us to go up this hill, giving us potential energy. When we're at the top of the hill, we have that potential energy, the ability we can move. It's likely that we're going to. And then here, when we lose some of that potential energy, we transfer that to kinetic energy. So it's a change. The kinetic energy, you're putting some energy in to get to a place to have some potential energy, just like the spring as well. You compress that spring, you put in some kinetic energy in order to get to a point where you have potential energy. So we're talking here about a transfer back and forth between potential and kinetic energy when you move things around and when you adjust the shape of things. It's a transfer of kinetic energy into potential, and then you can transfer that energy back out from potential to kinetic. All right, potential energy depends on the mass of an object, the force of gravity, which you may not know, but the force of gravity is 9.8 meters per second. You need to know that all the time. And it depends on the height of an object. This is called, we refer to this as gravitational potential energy, because it depends once again on mass, gravity, and the height of an object. M times G times H. M times G times H. or it can just be the weight of an object times the height. Because here on Earth, the mass of an object times the force of gravity, that's the same thing as weight, right? Our mass is affected by gravity, and that causes what we call weight. So you can either be given a weight of an object and then a height and determine its potential energy, or you can be given the mass, then you can multiply that times gravity and times the height to determine its potential energy. Weight is expressed in newtons in the metric system, so we have to remember that. Weight is always expressed in newtons in the metric system. And once again, gravity, 9.8 meters per second squared. You have to remember that number. It is a constant number. It's something we use in science all the time when we're talking about energy and the gravitational force that affects energy. So potential energy, once again, mass times gravity times height. Or if we already know the weight of an object, we can just multiply the weight times its height, and that will tell us how much energy it can have, or how much energy it has and can release or can use. Mechanical energy. Okay, that's the total energy because of the way an object is moving and because of its position. So if you've got an object that's already high and it's moving already, then you can talk about its total energy. You can talk about its total mechanical energy, total energy of motion and position together. So that's the way a hydroelectric dam works. It's based on potential and kinetic energy. We build this dam, which is this building right here, this large wall, on a river, and it causes the water level to rise. As the water level rises, we are obviously adding potential energy. And then when we release some of that water through the tubes, it transfers some of that potential energy into kinetic energy, and it spins a turbine. A turbine is kind of something shaped like a fan, so as the water goes by it, it spins. And then we use that kinetic energy and the potential energy that we have, so we're using mechanical energy, and we use that to create or transfer that energy into electric energy, because we cannot create energy. We just transfer that energy. So we add some potential, we transfer it to kinetic, and we spin this turbine, transferring it to mechanical energy, and then we transfer that mechanical energy into electricity, as you see here. These are electric lines. So, like I said, we cannot create or destroy energy. So, much like the law of conservation of matter, the law of conservation of energy states energy can neither be created or destroyed. It is only transferred from one form to another. So here, this is a pendulum. We worked with pendulums at the beginning of the year. And the pendulum just hangs when you're not messing with it at all. Then as you pull the pendulum up, you are adding potential energy, and then when you release it, you're releasing that potential energy. It transfers that potential energy into kinetic energy as it's moving, and then as it goes back up, it transfers that kinetic energy back into potential energy, and then the process begins all over again. It begins to fall again, transferring that kinetic energy back and forth as it transfers potential energy. As you go higher, you gain potential energy, and then when it comes back down, you are transferring potential back to kinetic, and then the same process once again is repeated back and forth. We are transferring energy from potential to kinetic. This is mechanical energy demonstrated by a pendulum. Once again, same thing here. When you go on a roller coaster, the coaster pulls you up to the top of the largest hill. That gives you potential energy. As you fall, you are transferring that potential energy into kinetic energy. Then as you get down here, you start moving back up, so you're transferring the kinetic energy back into potential energy. Then you get up here again, and then the process once again, you're moving, transferring potential back into kinetic. So it's a back and forth transfer of potential and kinetic energy on a roller coaster. So let's talk about some different kinds of energy now. We've talked about mechanical energy, which is potential and kinetic. Now let's talk about thermal energy. Thermal energy is the energy of the particles inside an object. The motion of those particles is what gives something what we call the thermal energy. So that's the energy of motion. We talked about adding thermal energy to a solid to move the particles faster. So as we give it more thermal energy, the particles are moving faster. And as we take away thermal energy, they move a little bit slower. Everything in the world is in some sort of motion. So everything has some sort of thermal energy. Once again, thermal energy is a kind of kinetic energy, obviously, because it is the motion of those particles. So the higher temperature something is, the faster the particles are moving. The lower the temperature is, the slower the particles are moving. Okay, and the faster they move, the greater kinetic energy. The slower they move, the lower kinetic energy. And that also relates to thermal energy. The faster the particles are moving, there's more thermal energy. The slower the particles are moving, there is less thermal energy. When you add or take away thermal energy, the particles are moving either faster or slower. That's what thermal energy is based on. Chemical energy. Chemical energy is a kind of potential energy. Something has the potential or the ability to release some energy, and it's the energy that is held in chemical bonds. When you make or break a chemical bond, you have to use or transfer some energy. So when you create a chemical bond, you have transferred some energy into that chemical bond, which is why gasoline can ignite and then release its potential energy that you have stored in it through those chemical bonds. The food we eat has energy stored in its chemical bonds. And when we eat it and our stomach digests it, we break down those chemical bonds and then we use that potential energy. We transfer that potential energy to us. So chemical energy is held in the chemical bonds of substances, and we break those chemical bonds and release that potential energy. Electrical energy, it's electrons moving. The moving of electrons is electrical energy. Sound energy. Sound energy is created by the vibrations of an object, and it sends waves through the air. As something vibrates, it kind of moves the particles in the air, and it transfers that movement through the air, through the particles in the air, and we take in that sound in our ears, and our eardrum vibrates, sends signals to our brain, telling us what that sound sounds like. So sound energy is an object that's vibrating, and those vibrations are transferred to the particles in the air and then transferred to our ears and transferred to other things. I'm sure we've all been around a car that had a lot of bass, and we could feel the vibrations of that bass every time it hits. We feel those vibrations because those vibrations had traveled through the air and traveled through other objects as a wave. Light energy, produced by the vibration of electrically charged particles. Okay, light energy, I think we know candles produce light energy. The sun produces light energy. Light bulbs produce that light energy, and light energy is also a kind of vibration of different kinds of particles. And we see light energy. We're not going to go deep into light energy, but you can see when there's light energy because that's how we see. So light energy is kind of obvious. Nuclear energy. Okay, we talked about holding energy in the chemical bonds of molecules. Nuclear energy is the energy that is held in the nucleus of an atom. So when you change the nucleus of an atom, you release some of that energy in the atom itself, in that nucleus. All that energy that's holding it together, you release some of it when you change that atom. And you can either split an atom, which is called nuclear fission, or you can join two atoms, which is called nuclear fusion. We use nuclear fission on Earth to create nuclear energy, and on the sun and other stars, nuclear fusion is the way nuclear energy is created. So it's actually a very small loss of mass when you're not supposed to be able to lose mass, but when you do, because it's such a huge reaction, it causes a lot of energy.